This video will discuss the solution to question 22. If the oscillator in figure 1 oscillates, the oscillation frequency f_osc in Hertz is, and then multiple symbolic expressions are given. This is the oscillator that we are going to investigate, and it consists of three major parts. We have a frequency selective network, beta, right over here, which consists of these three RC sections. We have a buffer, which is in the middle of the amplifier and the frequency selective network, which can recognize by the output of this amplifier being directly connected to the inverting input, so it has a gain of 1, and the gain network, which is this one. It's an inverting amplifier, and we can recognize that by the configuration. To investigate at which frequency this circuit will oscillate, we should have a close look at the transfer function of beta. The transfer function of the beta network will be given at the exam and is the following. To sustain oscillations, it's important to remember that we should satisfy the Barkhausen criterion. In other words, the open loop gain, which we will indicate by an L, or we can just indicate by the multiplication of our amplification factor and the impact of our beta network, should be 1. And since the amplification factor of A is always a real number, the beta network cannot have an imaginary part at its oscillation frequency. As a result of that, these two terms should cancel each other, and that imposes an additional constraint on the frequency of oscillation. And if you solve this for omega, you will get the frequency of oscillation in radians per second, which is the square root of 6 over RC. And we will indicate that this is the frequency of oscillation by adding a little subscript O for oscillation. The last step that you should take is reminding yourself that this is an angular frequency. To get to the absolute frequency, F oscillation, you should simply take omega at oscillation over 2 pi, which is the square root of 6 over 2 pi RC.